All right, so let's figure out the electron pair geometry. So we're going to count around selenium. We've got 1, 2, 3, 4, 5. Okay, so we've got 5 regions of electron density. What that tells me right away is that I'm going to take on an electron pair geometry of trigonal bipyramidal. Okay, so I'll go ahead and draw the outline here. Okay, now I've got a decision to make. I need to figure out where I want to put that lone pair of electrons that's hanging out on that selenium atom. Do I want to put them at the equatorial position or the axial position? Okay, so it turns out the best place to put the electrons is at the equatorial position. So place lone pairs at equatorial position. And the reason why we do this is that this minimizes repulsion with other bonds and other pairs of electrons, okay? If we had more than one lone pair, we would put it here or here, okay? So we just keep putting it at those equatorial positions to minimize that repulsion. Okay, so I am going to put the lone pair here. I could have picked the other positions, but I'm going to pick it right here and at the equator, and we'll put the chlorines on the other positions. And here we're going to say that we have a 90-degree angle between the axial ligand or axial position and the equatorial position, and we have a 120 at the equatorial. And this shape is actually known as the seesaw geometry. So our molecular geometry is seesaw. Sometimes people call it the sawhorse. Okay. All right. Now let's check out what happens when we have more than 5 regions. Okay, so we're going to look first at SF6. So we figured out that Lewis structure was something like this. So many electrons, gosh. Okay, so let's count the regions of electron density. 1, 2, 3, 4, 5, 6. All right, 6 regions. In this case, the best arrangement to have 6 regions of electron density is something called the octahedral geometry. Okay. So in this case, I'm going to have 2 going up and down, 2 going out at you, which are the solid wedges, and then 2 going back into space, which are the dashed wedges. Okay. And in this case, I don't have any lone pairs, so I only have one decision here in terms of where to put things. I'm going to put those fluorine atoms on all those positions. The angle is 90 degrees in all cases. And for this, we would say that our electron pair geometry and our molecular geometry are both equal to octahedral. Okay, not too bad. All right, now let's see what happens when we have some lone pairs going on. So let's take a look at xenon tetrafluoride. Okay, so first start with the Lewis structure, and again, this is something you got to do previously. We worked through this in class, so we figured this out, and we've had basically 4 bonds, 2 lone pairs around that xenon atom. So let's count the regions of electron density. 1, 2, 3, 4, 5, 6. Again, we've got 6 regions of electron density. So we're going to say our electron pair geometry is octahedral. So we'll go ahead and draw our outline. We've got 1 going up, 1 going down, 2 coming out at you, 2 going back into space. Okay, now we've got to make a decision as to where we want to put those lone pairs of electrons. Okay, and again, we have to think about these lone pairs really don't like being close to one another. Okay, they're like fighting siblings. So we need to take them and put them as far apart as possible. Put them in separate rooms. Okay, and it turns out, let's just put one on the top here, and then let's put the other one clear on the bottom. All right, we just want to get those away from each other as far apart as possible because there's a lot of repulsion because they have those negative charges. Okay, and then we'll put the 4 fluorine atoms on that plane there. Okay, and notice that this forms kind of a square shape, and so that's called a square planar molecular geometry. So our molecular geometry is square planar. Okay. So now, I didn't go through every single one of the examples in the handout, but that should get you at least a little bit more familiar with what's going on. Now we're ready to talk about polarity. And this is an important property of a molecule which essentially determines its chemical properties and its reactivity. So it's pretty important. So let's first remind ourselves of this concept of electronegativity. Okay. So let's suppose we have a covalent bond, HF, and if every atom had a similar pole or a similar nuclear charge, they would share those electrons equally. But instead, what happens, because fluorine is sort of up and to the right on the periodic table, it's got that high effective nuclear charge, and so it's going to have a greater pull on the electrons. So electrons are going to be hanging out on the fluorine side of the molecule more than they would be on the hydrogen side. Okay, so what's going to do is it's going to cause a partial negative charge to build up on that fluorine side. It's not a full negative charge like you would get like in an ionic compound. It's just a partial, okay, because it's not completely on that side. And then we will have a partial positive then on our hydrogen. Okay. Another way to represent this is to have something called a bond dipole moment. And that's drawn like this. So you have an arrow. The arrow points to the negative end of the molecule. And then the cross here is on the positive side of the molecule. Okay, so now we want to know what happens in 3 dimensions, okay? What if we have more than 2 atoms and we have these things hanging out in 3-dimensional space? How do we figure out our polarity of that molecule? So let's take a look first at carbon dioxide. And we had this as one of our Lewis structures. And it's a linear molecule. So again, before you do the polarity, you really need to kind of figure out what the shape is first. All right, so let's take a look at how the dipoles play out here. Well, you want to have a periodic table on hand, and if you notice, oxygen in the periodic table is more electronegative, has a higher effective nuclear charge than carbon. So because it's more electronegative, we're going to have a partial negative on the oxygens and a partial positive on the carbons. Okay. And so what this does is generates a bond dipole going in this direction, but also an equal and opposite bond dipole going to the left. All right. And so in physics, if you have 2 forces that are essentially opposing each other in different directions, the net force is going to be 0, right? If they have the same magnitude. So we're going to say, in this case, there's no net dipole, because those dipoles cancel. And because of that, we're going to say that CO2 is a nonpolar molecule. All right, so now let's look at something like water. Well, water we found that water was actually a bent structure. It's not a linear molecule. And again, with your periodic table in handy, you can figure out that oxygen is more electronegative. So it's going to take on a partial positive. And the hydrogens are less electronegative, so they're going to be partial positive. And so what we're going to get in this case is we're going to get a bond dipole pointing upwards here and another bond dipole pointing upwards here. Okay. And essentially the horizontal components of those dipoles will actually cancel each other out, but you can see that there's actually a net dipole moment which is pointing upwards. Okay. So in this case, we do have a net dipole or a net polarity. So water would be an example of a polar molecule. Okay, and this is actually super important. I mean, if water was not polar, life as we know it really wouldn't exist. I mean, everything relies on the polarity of water in that context. Okay. Now let's check out some cases where some of those more complex cases. So let's check out xenon tetrafluoride. I'm going to give myself some space here. So xenon tetrafluoride we saw was this square planar shape. Okay, so let's draw our fluorine atoms in there. And let's figure out our individual dipoles. All right, we know that fluorine is more electronegative than xenon, so we're going to have dipole moments which are pointing to each fluorine atom. we have something like this. And you don't, when you see those lone pair of electrons, you don't draw a dipole moment with that, because the electrons are essentially just, they're just hanging out on that xenon. And what you want to think about more is the nuclei, or the positive charge, which is pulling the electrons towards those atoms, okay? So they're not going to affect the dipoles in this case. So if we look at this shape, because of its symmetry, the dipole moments on those fluorine atoms are essentially going to cancel each other out, okay? So in this case, our net dipole moment is going to be 0. So this xenon tetrafluoride would actually be a nonpolar molecule. All right, let's check out selenium tetrachloride, because we just did that structure. Okay, so let's redraw it here. We've got our seesaw shape here. Okay, let's figure out what our dipoles look like. So we're going to have a dipole pointing upwards because of that chlorine, and then also downwards here, okay? So those dipoles, actually, we got one going up, one going down. Those are going to cancel each other out, okay? So if we had no other atoms sitting around, then that would be an example of a nonpolar molecule. But we do have some chlorine atoms hanging out in this this equatorial plane, and that is actually going to produce a net dipole moment in this direction, okay? So it's basically, you can see that due to this asymmetry, this asymmetric nature of this molecule, we have this lopsidedness, which causes electrons to sort of hang out over on this side of the molecule, okay? So in this case, selenium tetrachloride, because of its molecular geometry, because of its shape, we see that it is actually a polar molecule. Okay, so whenever you're asked to figure out whether a molecule is polar or nonpolar, you need to figure out its shape, okay? And you need to consider how those dipole moments are going to cancel out or not, okay? All right, so hopefully this gets you guys up to speed. I apologize for the little hiccups here and trying to work with this program, but please let me know if you guys have questions. Come see me, and I can try to help you guys get caught up. So, all right, okay.